Hi, my name is Leszek. I'm from the V8 mobile team in London, and I'm going to be talking to you about caching more JavaScript code in Chrome. I was supposed to be co-presenting this with Maitri, who unfortunately couldn't make it today, which is a shame because most of this work is hers, so I'll do as a good job as I can presenting it myself. So let's talk about JavaScript code execution in Blink. When Blink has to execute a piece of JavaScript code, first it sends the source code of that script to V8 to be compiled. V8 returns a compiled script, and then that script is passed back to V8 again to be executed. Now, when I say that the script is compiled, that means that there's a couple of stages to it. There's a parsing stage where the script is parsed, and then there's a separate compile stage where the script is compiled. This happens for the top level script, and it happens again for a couple of inner scripts as well, inner functions of that script as well. So why do we want to cache code? Why am I giving a talk about code caching? It turns out that these parse and compile stages actually take up over a third of time spent in V8 in total. So they're prime candidates for things that need to be sped up, and the best way to speed something up is to not do it at all. So we have a couple of different types of caches in V8 and in Blink. The first kind is isolate caches that we store in V8. So an isolate cache is effectively a hash table that's stored by V8 on the V8 heap, which maps sources to compiled code. So when a script compilation happens, that script compilation will generate some amount of data in V8 on V8's heap that V8 will use later for execution. And we opportunistically store that along with the source, keyed by the source, in a hash table. So that the next time a script is executed, if we see that source code, we look up that source code in our hash table, and it's the same one, then we just take the same code that we had before and give it straight back to the script compilation, pass that up to Blink, and everything happens a lot faster because we don't actually have to do the compilation at all. And this is basically for free, modulo a hash table lookup, but effectively it's for free. It's really great, and it has a really high cache hit rate, 80%, which is wonderful. But it can be improved. It can be improved by 20%. And the biggest problem with it is tabs. I mentioned that this isolate cache was owned by V8. It's on the V8 heap. We have different instances of V8 between different renderers, which means that if you have two tabs with two different renderers, both loading the same script off of a jQuery off of CDN, then one of them will try to compile it. It will see it in its isolate cache and will happily load it very quickly. The other tab, it doesn't have the same isolate cache. It can't make use of the same optimization, and it has to do the parsing compilation stages itself, which is a bit of a waste. So we have a second tier of caching on the actual resources, metadata on the resources stored by the browser. So the browser has a resource cache, which it uses for network requests in general. And on a cold run, when we ask the browser, or when the browser navigates to a particular script, it caches that data, and it has an associated metadata field, initially empty. When we execute that script, we just throw in the current timestamp into that metadata for later, and we proceed as normal on a cold run. On a warm run, which is the second time we see that script, we see the timestamp in the metadata, we read it off. If it was a long time ago, where long is 72 hours, then we just count that as a cold run and we rewrite the current timestamp. Otherwise, if it's within 72 hours, well, we compile the script as before, and then we additionally create a serialized form of the compiled code in a serialization step, which we send back to Blink. And Blink IPCs that across to the browser to be stored in the code cache in the metadata instead of the timestamp. And then we proceed as normal. On a hot run, the third time we see this script, we load the code cache from the metadata. We see that it's valid and all these a couple of these checks. And then we send that cache code along with the source code to V8. Then V8 can deserialize it onto its heap and execute it as normal. And again, this is reasonably fast. It's not as fast, obviously, as the isolate cache because it's not opportunistically in memory already. We have to do a serialization. We have to do a deserialization. We do the serialization in a warm run instead of in a cold run because we won't necessarily see the same script multiple times and we don't want to waste time serializing it. But overall, we do get the benefits. And if we have two different tabs that are loading the same script, then they can both take advantage of this code cache because it's IPC between processes and it lives in the browser process. And this has a cache hit rate of 80%, again, of those 20% that we haven't hit already. In brackets, I've got here of cacheable code because not all code is unfortunately cacheable. So of the codes that we can cache, we hit 80% of them. In fact, we have 80% of our runs are hot runs. And you can see that we have more cold runs than we have warm runs, which means that about 3 times more, which means that there is a lot of code that we only ever see once and we don't want to waste time serializing it. So I called this this talk caching more code, JavaScript code in Chrome. What do I mean by more? What I described was the state of affairs up until essentially the start of this year. But one small lie that I told you was about JavaScript execution in Blink. This parse and compile of inner functions. So I'm going to take a small step back into how scripts are compiled in V8. When we see this top-level script, we compile it into bytecode, internal bytecode that we have. We store that as a shared function and info piece of data, a structure with some additional metadata relating to the script. The details here aren't really important, but we do that for the top-level code only. And then the inner functions of that top-level script are stored as separate functions on the heap. So our top-level script will have a list of constants. Those constants will include the inner functions, and those inner functions have to be compiled as well. But for some functions, we don't necessarily think that we'll end up compiling them initially at all, that we won't need to execute them at all, so we don't necessarily have to compile them in the first place. Library functions, callbacks, event handlers, all these sort of things, we don't necessarily need them immediately. So we don't want to spend that expensive 33% of our time parsing and compiling them. So instead, we have lazy compilation of some inner functions, where we essentially try to run through the function as quickly as possible, collect as little data as we need, and try to find that closing curly bracket to skip that function where we can. So instead of our shared function for containing a bytecode, it just contains a marker saying, hey, when you see this, compile it lazily, plus some additional different metadata. Other functions, we might know that we will need it immediately. They're still inner functions, but they're what we call immediately invoked function expressions, IFEs, which means that they're function expressions that are immediately invoked. And this is really just a heuristic for us, but we look at this opening parentheses and say, well, we reckon that this is a function expression that we're going to call straight away. The pre-parsing step that I described previously is cheap, but it's not free. So if we can avoid doing it and just do the straight up parse straight away, then we would prefer to do that. So these functions get compiled eagerly, just the same as the top level script does. And you end up with a bytecode that has a list of constants. Some of those are lazily compiled functions, some of those are eagerly compiled functions. And then you get to the actual execution. And during that execution, we will maybe call one of those functions because it's a library function that we need immediately. We're generating a handler file here. And we'll say, hey, suddenly we need this function now. It was marked for lazy compilation, so run through it again, compile it properly, create some bytecode for us. And oh, look at that. It has an inner function, so that goes into our list of constants. Does it have a opening parenthesis in front of it? No. Well, it's not an IFE, so compile it lazily. And you end up with this tree of functions on the V8 heap, some of which are lazily compiled, some of which are eagerly compiled. and some of which are needed during execution, others aren't necessarily immediately needed. So what I told you about JavaScript execution in Blink, yes, you parse and compile the top level script, but some of the other functions you might skip. However, some of those skip functions you might end up needing during the script execution, the top level script execution. So you end up parsing and compiling them during the run script phase, and we've wasted time because of heuristics. Heuristics are never perfect. And it means that our serialization step, it only really cares about the compiled functions. So our skip functions, except for some small amount of metadata, are not in the serialized code. Which means when we deserialize it, we still have to parse and compile those functions during script execution. So one thing we introduced this year, now I believe in stable, is caching after execute. So on a cold run, we will write the timestamp and execute the script as normal, skipping where appropriate. Same as before. On a warm run, we read off that timestamp and we execute as if it were a cold run. But after that execution, we have a separate cache creation step, which runs after both compilation and running that script. And that's what creates the code cache now. And that's the code cache that actually goes in to the resource cache, metadata. Which means that on a hot run, we can read off that code cache and we can execute the script. And now, because we've already compiled everything that we needed during execution, we don't need to do any more compilations during the hot execution, which speeds that up a little bit. Why didn't we do this before? Well, it's to do with the old compiler versus the new compiler. You might remember from previous BlinkOns or previous V8 blog posts that midway through last year, we introduced a new compiler. So the old compiler generated machine code from source code, the old first-tier compiler. And this is a simplified explanation of the machine code that it generates. The fact that I still have to use x86 assembly on a slide to give you a simplified explanation is sort of indicates why we changed compilers. And this machine code, it has to go through all the various JavaScript semantics that we have of property lookups through prototype chains and whole values and undefined values. And it can be slow. So the thing that made V8 fast when it was released in 2008 was inline caching of machine code, where we would look at execution that happens and we'd say, hey, this is always loading the 0th element off of an X object. So this call that we have to an unknown property load, we can patch that, physically patch it in the generated machine code into a specialized call that checks if we're doing the things that we think we're doing and has a fast path for them. If we know that we're always adding 2 strings, then we fast path into a string addition. And again, we have to patch the machine code to call a different function than it did before, which is great, and it made V8 fast, but it meant that the machine code was context dependent and it was execution dependent, which meant that the machine code changed after script execution. So we couldn't serialize it after script execution because it was the wrong machine code, or was specialized machine code for that case. The new compiler compiles to bytecode instead. And that bytecode has indices into what we call a feedback vector. So when we load a property off of a particular map multiple times, then we write, oh, we're always loading the 0th offset into the feedback vector. If we're always adding 2 strings together, we write down the feedback that these are always strings. And the important thing here is that the bytecode itself does not change. The bytecode is context independent, and the feedback vector is context dependent. So if we're only serializing the bytecode, we can do it after execution, and it's still the same thing. And code caching after execute has given us great improvements in compile time in real-world scenarios. We've had up to 60% decrease in overall compilation time which is both compilation time during actual compilation and during execution, up to 60%, average 20 to 40% improvement in compile time. This is on our top 25 benchmarks. We've had similar results from the wild, from UMA.
Compilation is
no, yeah, please.
No, but I was just wanted to ask if compilation is parsing and
Yeah, parsing time has decreased even more, partially because we're skipping some of the pre-parses that we don't need to do. So this has been a wonderful improvement from a relatively simple change enabled by the interpreter, which was also our team in London. Another thing that we're looking at is caching inline scripts. So I mentioned this resource cache that happens for JavaScript files if you load them with a script tag that has a source that is an external JavaScript file. What happens if you have a JavaScript directly in your HTML? What happens if you have two different scripts inside of your HTML? Your HTML response is in the resource cache as it was before, but we can't just have a single script's code cache in the metadata because we have multiple scripts. So up until now, inline scripts, well, actually still now, inline scripts are not cacheable. When I said that 80% of our cache hit rate is 80% of cacheable code, inline scripts were one of those non-cacheable codes. And this kind of sucks because inline scripts actually take up a whole chunk of our compile time on both Android and Windows. Almost a quarter of our compile time on Android is spent compiling inline scripts. So something we're experimenting with now, and by experimenting I mean we're running a Finch experiment now, is storing a table in the metadata, a serialized hash table from source code to code cache for each individual HTML file. So that when we see a script inside the HTML, we quickly run through its source, and if it matches our hash table, then we load the code cache or the timestamp from this metadata. Why are we using sources rather than indices or offsets within the code? Because HTML is complicated, and you can document.write new scripts, or you can add new script elements. It's actually quite difficult to figure out what script element you're using and if it's deterministically going to be there in the future with the same offset. So sources seem safer. And because we don't actually want to store entire string sources in our metadata table, we just store a crypto hash of those sources.
So that only works if the HTML is identical to the previous HTML?
It only works if the JavaScript source within the HTML. Well, I mean, this will only work if this HTML is sorry, still running cached off of the network cache. So if the HTML file changes, then this, if the script.js file changes or the HTML file changes, like it gets wiped out of the resource cache anyway.
The inline scripts haven't just
That's how it goes. I'll talk a little bit about that in our next work. But yeah, we store a crypto hash, a SHA-256 hash of the source, and pray that there's no collisions, or that a meteorite will hit the user's computer. 256, yeah. A meteorite will hit the user's computer before they get a hash collision here. So I think we're safe. So yeah, what happens next? There's caching more scripts. As I said, this is running still in Finch experiments. We're expecting a 5 to 10% improvement in compile time again. And well, we'll see how it goes. Ongoing work. Yang. I believe they will. In that case, I believe they won't. I would have to double check that. But they could use the same mechanism. I mean, at the end of the day, we're just looking at source strings then. So a lot of things could go through the same mechanism if it starts to work. So caching more scripts. Inline script compilation obviously takes a long time currently. What takes more time on Windows is other, a big bucket that I wish I'd split up when I was doing this data collection. But from what we can tell, it's predominantly predominantly extensions on Windows. Things like modules currently going through a different code path. Small code that's smaller than a kilobyte doesn't get cached for, again, historic reasons more than current reasons. So that's a heuristic that we might want to revisit. But there's still plenty of work there to be done. I mentioned that we're just using this source table, which means that we're not sharing things between HTML files that change, or pages that reuse the same chunk of inline script code between pages. So it'd be nice if, well, like in this case, you have two pages. They both use the same script, but they store two different tables, both pointing to the same code cache or similar code caches. So it'd be nice if we could just store those by the source in the resource cache itself. That's additional engineering complication. It's not logical complication, but there is engineering complication in using something that was fundamentally a network-based cache and change it into a hash-based cache. And that's what we're focusing on. We've been seeing great improvements from code caching so far in the real world, and we're hoping to see more of them in the future. I'm happy to take questions.
I'm from UZ browser. I do exactly the same thing that you did last
Great.
year.
I'm sorry we're so behind.
The inline script catching also.
Great.
But we don't do it in the browser. We do it inside the engine and then Viva platform interface.
So you do it in the renderer, you mean?
There's an interface called the V8 platform. Recognize that? We add some new method inside. Say catch something.
Oh, I see.
And they just say that inside the app.
Yeah. So because of
same HTTP cache side.
Yeah. Yeah, I see where it came from. You go through the cache in the V8 platform interface.
Yes.
Yeah, because of the layering that we have in Blink, that's probably not an approach that we can take without terrible refactoring or layering violations. But yeah, it's a perfectly valid approach, and I'm happy you could do it.
Yes, and we also cache if the script hash is the same, we take the same, and we take out that cache.
Well, that does mean that it seems like the right solution if we both came to it independently. That's great. Yes.
What's the memory footprint?
Great question. The eviction policy is the same as the network cache policy. So that hasn't changed. We haven't changed that.
So it's tied to cache control?
Yeah, it's tied to HTTP caches. The size of the serialized code is roughly on par with the size in memory of these scripts, because they're essentially just like the bytecode is just mem copied into the serialized code, which is, I want to say, about 1.5 to 2 times larger than script sources. Caching after execute increased, I think, serialized code size by roughly 80%, but the deserialization is about 10 times faster than compilation, so we consider that to be a reasonable trade-off. These are all numbers that I'm reading from memory, so they might not be entirely accurate, but it's that sort of order of magnitude. If you run Chrome for a week, well, I mean, depends on your cache eviction. It depends on what websites you're visiting and how long their caches last. The code caching existed before, and it was, I guess it would have been roughly doubling disk cache memory, and then yeah, the caching after execute would add more.
In memory, like for the entire browser, the JavaScript cache is in memory, or is there this?
Now, let me make sure I get this right. We have 2 copies of some of this data because it's being IPC'd between the browser process and the renderer process. The one on the browser side is in memory temporarily, like just for reading off, predominantly on the disk cache, and I believe there's some work to map it. The one on the browser is kept in memory the source is kept in memory as long as the script is alive because we still need it for the function prototype to string and things like that. Yeah. I'm not 100% sure on the details there because I've mostly worked on the Blink side of it.
So generally, I think that not relying on the HTML, not changing, will significantly improve the caching of inline scripts because first, there are many cases where people just go from one page to the other and the scripts are the same, but pages are.
So going from one page to the other, I think, is actually the cause of our high cache hit rate in isolate caches. If we hit the isolate cache, then we actually don't do any more work. And it's the same renderer because we're on the same page. You just click the link, and so we'll have the same V8 isolate, and we can just pull stuff out from the same hash table.
Okay. Even if so also for inline scripts.
Yeah, inline scripts are in the isolate cache. Every script object that we see, it goes into the inline cache, including ones that are still not cacheable by the renderer, by Blink. Yes. Yeah, same sort of thing. If you don't want that, then I believe service workers are the solution. Service workers also don't have the pre-parsing that I described. I think as of 67, they won't have the pre-parsing, but we just eagerly compile everything in the service worker script. Yeah, and it's that sort of inlining that actually made us like really look at this, because our previous assumption, the reason we didn't work on inline script caching before, was this assumption that inline scripts are just 5-line add scripts that we can compile pretty quickly. When we realized that Webpack will inline big scripts, and Facebook obviously is gonna inline things that they don't want to do two network requests for. We were like, oh yeah, actually inline scripts take a whole bunch of time and they take a whole bunch of size and they're worth looking at. Right. Yes. That's interesting. We don't do that yet. Is it no store only if the cache is cold, or is there any sort of heuristic like that, or is it just a entirely separate thing? I mean, if it doesn't exist in the cache, then in the network cache, then we won't be writing metadata to it anyway. We'll send up the timestamp, which is cheap to send, and we won't be able to read off that timestamp again on a warm run. But yeah, I mean, that sort of stuff is not yet fully investigated. So there might be similar kind of issues. If we see serious regressions in, I don't know, in compilation time without seeing those caches being consumed, then yeah, that's the sort of thing we would look at.
What happens with revalidations?
Revalidations clear out the metadata.
Okay.
Failed revalidations clear out the metadata.
Oh, failed. Okay.
Yeah. Normal revalidations just preserve the metadata. Same as they preserve the data of the actual response.
What's the engineering reason you don't use the hash of the script content as the key for the table? Because I know that there's lots of framework outside, so the different side may use different URL, but actually same content for the framework. So and the reason I know that's if you actually have the same hash for the different URL is that if in the code they actually try to output the stack trace, they actually if they you compile the cache of URL1, but in the end actually the cache be using in the URL2, the stack trace will give the wrong information, but that problem can be solved.
Yeah. I see where you're coming from. There's a couple of engineering reasons. Like one of the engineering reasons is obviously that just refactoring is hard, and we had this existing cache which we could attach metadata to. It was the easiest way of doing caching. A bigger problem that's less of an excuse is that it makes cache invalidation a lot harder, because currently we're relying on the same cache invalidation as the HTTP cache headers, provided by the user. Now, if we were to do that sort of thing, we'd have to kind of get the max of the expected lifetime or something like that.
The code cache, JavaScript cache, from the network cache, it should be possible. Right?
Yes, yeah, absolutely. But it comes with that engineering problem, but it is something that we want to look into. It's just not been something that we've had the headcount really to look into yet. Yes, Brad. Completely crazy. Completely crazy because it will include links to things that are on the V8 heap. So yeah, and maps that have been generated on the V8 heap. So we'd have to do some sort of translation for those, or yeah. I mean, it's the same reason we would have had to clear the machine code previously.
Is there something origins can improve caching, or cache ahead of time, or
well, don't do what Facebook does and don't change your codes as often. In all seriousness, yeah, I mean, it's a cache, so don't change things. There's not really much more that you can do. Pack stuff together, I guess, into single scripts, because then they're more likely to go over the 1 kilobyte threshold for small code. Previously, I would have said don't use inline scripts, but hopefully that's something that we'll be able to fix now. External scripts will still be better at being cached, because they won't be tied to an individual HTML file. But yeah, it's that sort of level of thing. Or use service workers if you know that you use service workers to load in your actual JS files, because then they'll get eagerly compiled. And they'll be cached, I believe, one step earlier. I think you can correct me on that, Kawhi. It's been re-enabled. It got re-enabled, I think, yesterday. I think it got re-enabled yesterday or today. Yeah. It was re-enabled recently anyway, I believe. So yeah, as of 67,
so if
you'll have that
I'm
you could compile.
downloading script files from the service worker,
Yeah. If they're cached in the service worker, they're also
if they are
get,
cached in the
yeah.
service worker,
Yeah, they'll get you. I'm less of a good person to talk to about that. You want to talk to the Tokyo team, because they've been doing most of the work there. But yeah, that's how I understand it to be. Hey.
It doesn't work. It's caching modules.
Hmm?
Caching modules doesn't work yet.
Not yet.
No, it's not implemented.
Nope.
And,
That's why it was in the other bucket.
Yeah. You should fix it.
Yes.
Great talk. Thanks. Thank you for working on this.
Oh, yeah,